Determine whether or not Rolle's theorem applies to the function f on the given closed interval between a and b. If Rolle's theorem does apply, find all values c within the open interval between a and b for which f dash c equals 0. Right, and you've been given two functions. So just before I talk about the functions, Rolle's theorem says that if you have a function such that every element in the domain maps to a real number, that function is continuous on the closed interval between a and b, and it's differentiable on the open interval between a and b. So if those conditions are all true, if f of a and f of b both equal 0, so the values of the function at the ends of the interval that you're interested in, if that is true, then there exists a c within the open interval a and b, so a c between a and b, such that f dash c is 0. So if I just explain that really quickly, say we just had x and y, and we've got a and a b such that f of a is 0, f of b is 0, then basically a continuous function just means you draw it without taking your pen off the paper. So if you think about how I can get from a to b, there's no way you can draw one continuous line from a to b without at some point having a horizontal tangent. You just can't. If I go around here, anytime you change direction, you're creating a stationary point. If I just went straight there, well then it's always horizontal, for example. So whatever I do, I'm going to have these points. Here's a c here such that f dash c is 0. You could have a c here such that f dash c was 0. So it's just, again, it's similar to the intermediate value theorem. It's kind of a common sense theorem to do with continuous differentiable functions, but it's written as a theorem that you can cite. So our first f of x is f of x equals 3x cubed plus 5x squared minus 43x plus 35 equals 3x cubed plus 5x squared minus 43x plus 35, and the interval, the closed interval we're interested in, is between -5 and 2 1/3. Just like that, right? So the question says, does Rolle's theorem apply? Well, if you think of the nature of the function, it's just a nice cubic. There's no surprises in there. It's continuous everywhere, and it's differentiable everywhere. So let's write that. F of x is continuous and differentiable for all real x. So that's a good start. So two of the conditions have been met already. We then need to see, well, what's the value of f of x at -5 and 2 1/3. So something like that, given that, remember, time's a real factor in these exams, you don't really want to be doing a whole substitution. We just need to know what is f of -5 and what is f of, well, it's 2 1/3 is 2 times 3, 6, 7/3. What are these values? We're hoping they're both going to be 0. If they are 0, given that this is true about the continuous and differentiable nature within the interval, if all of these things are true, then yes, Rolle's theorem applies, and there's at least one c such that f dash c is 0. So if you want to do this quickly, the easiest way is just to, I would suggest, say there was nice numbers, you might use a table. But actually, as good a way as any is probably just to put the function into the graph, which I've already done actually. If you just put the function into the table or to the graph mode, you can then just draw it and use the trace function to tell you the value of f of -5 and f of 7/3. So the function looks like that. So the question wasn't, can you see how many places, well, it will be later, but it's not asking me, look at the graph and tell me if there's any zeros, but there obviously. You can see a 0 in f dash x here and here, but that's cheating. We need to use the theorem. So what I want to know, what is the value of the function at -5 and 7 over 3. So if I just put shift trace and put in the value -5, so when x is -5, y is 0. So that's a good start. And then we need to do the same thing for 2 1/3, 7 over 3. 7 over 3. So f of 7 over 3 is also 0. Right, so now that is true. We've talked about it being continuous and differentiable, so yes, Rolle's theorem does apply. So yes, Rolle's theorem does apply, and then it says, if Rolle's theorem does apply, find all values of c within the open interval between a and b for which f dash c equals 0. So we're probably going to need f dashed x. F dashed x, simple enough. One is just polynomial, so it's going to be 9x squared plus 10x minus 43, which, if you look at that, there's no common factors to pull out. It's a bit nasty, actually. I don't think it's going to factorize. That being said, you'd probably go for the formula or for a quadratic solver, something like that. Or given that I've got it on the graph, I could probably get it up like that. But if we want exact values, you're not going to get those from the graph. So what we could do is use the quadratic formula. So if 9x squared plus 10x minus 43, if that equals 0, then that means x equals minus b minus 10 plus or minus the square root of b squared, that would be 10 squared, 100, minus 4ac, so you've got a negative there, so that would be plus 4 times 9 times 43. Huge numbers we're dealing with here, all over 2a, well that would be 2 times 9, which is 18, so not the nicest number in the world. So if we go to our calculator there, we're going to have minus 10 plus the square root of 100 plus 4 times 9 times 43 all over 18. So that's one of the solutions, and it's not very nice, as you can see, so I think we made the right choice to not even attempt to factorize the thing. So x equals, well, the first solution, probably I might put over here, because I added first, so x could equal minus 5 plus 2 root 103 over 9. I say x, it's not really x, is it? We're talking about c, because we're looking for the values of c such that f dash c equals 0. So the second solution will come just from going into here and changing the plus to a minus. So the other solution is x equals minus 5 minus 2 root 103 over 9. Okay, the second function, f of x, is the absolute value of x minus 5, and the closed interval is between minus 5 and 5. So f of x equals the absolute value of x minus 5, and we're interested in minus 5, 5. Right, so if you remember, not long ago we did look at the absolute value of x, and we assessed it for continuity and differentiability, and it had a problem. It was continuous everywhere, but it had a problem when x equaled 0. If we just have a look at the absolute value of x at minus 5, well, the absolute value of x would do something like this. It would be f equals minus x here, and it would be f equals x here. If we then take away 5 everything's going to go down to 5. So it looks like that. F of x. We have minus 5 here. And if you think about these x-intercepts, remember that's when y equals 0. So when does the absolute value of x minus 5 equal 0? Well, the absolute value of x would need to be 5. So x could be minus 5 or 5. Minus 5 or 5. So thinking about applying Rolle's theorem, some conditions are definitely met because f of minus 5 does equal 0. And f of 5 equals 0, right? So the condition are that at the end point of the closed interval, that the function needs to take the value of 0 at those points. So that happens. The problem with this is that f of x is not differentiable at x equals 0. So you can see that if x is greater than or equal to 0, when we're going towards 0 from that way, f dashed x is 1, right? So if x is greater than or equal to 0, f dashed x, when we look from the right hand side or from something greater than 0, equals 1. So all the way on this side it equals 1, and if we look the other side, if x is less than 0, f dashed x from the left hand side or from less than 0 equals minus 1. So that is showing us that it's not differentiable in this open interval. F of x is not differentiable for all x in the open interval from minus 5 to 5. And once that's not the case, we cannot use Rolle's theorem. Rolle's theorem does not apply. So it is continuous everywhere, but it is not differentiable everywhere. And if you think about it, actually there is no place where f dashed x is 0 between these 2 points. That would be the point, say this was some normal function that goes down and then it comes up again. You would expect a turning point with a continuous function, but the fact you've got this issue here, as in it's not differentiable here, you can see that's clearly not a stationary point.